the fourth postulate that we'll be considering in quantum mechanics has to do with how we find average values of observables. So as we saw with the momentum operator in the particle in a box, we won't always find wave functions that are eigenfunctions of the operators we care about. Right? With the momentum operator, we showed that we saw that there are no eigenvalues with the eigenfunctions that we found, the wave functions we found for the energy, right? And so if we want to find things for things that are not eigen, right, that don't fall from postulate 3, if we want to find average values, so the average value of an observable is given by the following equation. And we've already seen this with the momentum and position operators we looked at in the last chapter for the particle in a box, but this is now generic. The average value of A is that we integrate over all space psi star the A operator that corresponds to that observable psi d tau, where d tau again here represents all the possible variables for our system. This just makes it so we don't have to specify x, y, and z, or r, theta, and phi, or just x for a one-dimensional problem. We can just be generic here. Okay, and so that's the postulate, and we've seen this in action already with finding that the average momentum of a particle in a box is 0. We can look at this with more complex examples. So let's go ahead and do that. So we'll look at example 4-4 from your textbook. So when we get to chapter 5, we'll find that one of the wave functions for the harmonic oscillator is this function here. So psi 0 of x is equal to alpha over pi to the 1/4 e to the minus alpha x squared over 2. And this is over the range from x goes from negative infinity to positive infinity. And so we might ask, what is the average momentum of this? And I'll just tell you in advance, we're going to do a lot of work to get 0 again. And I'll be more specific, the average momentum in the x direction. But let's go ahead, right? We can write out the expression for this. All right, so this is defined only in the x coordinates, so we only need to worry about x, but x ranges from negative infinity to infinity, so we need to write, those are the limits of our integration. And it's going to be psi star px psi dx. Okay, and so then we just plug in our wave functions here and our operator. So we have this alpha over pi to the 1/4 e to the minus alpha x squared over 2 negative I h bar derivative with respect to x alpha over pi to the 1/4 e to the minus alpha x squared over 2 dx. Okay, and so this is the problem that we need to solve. So let's go ahead and pull out all the constants that we have here. So we have our alpha, and this is something I always like to do to just kind of keep track of what's going on in a system, is anything that doesn't involve our variables, we can just pull them out and take them separate. All right, so I'll end up with alpha over pi to the 1/2. We don't actually know what alpha is, but it ends up not mattering for this problem. And we'll have an I h bar. And then let's go ahead and do this derivative. Right, so derivative of e to the minus alpha x squared, we're going to get 2 alpha over 2 as another set of constants. Right, so this derivative here is 2 alpha over 2 e to the minus alpha x squared over 2, right? We'll get the same derivative back. Okay, so we'll end up with integral from negative infinity to positive infinity e to the minus alpha x squared over 2 times e to the minus alpha x squared over 2. So we just have the same function twice. Okay. Oh, and an x. I'm missing an x here. 2 alpha x over 2. Okay. I knew something didn't look right. This happens when I don't look at my notes. Make sure I don't mess things up. Okay, so we have all of our constants. I'll just write them as constants. integral from negative infinity to infinity, x times e to the minus alpha x squared. So when we multiply those exponentials together, the things up in the exponent multiply together, or they multiply together, so there's two of them, so it's like the same thing as squaring it. Okay, and so right here I'm going to introduce a technique that's very useful. So x is what's known as an odd function, and e to the minus alpha x squared is an even function. Now, what do I mean by this? Well, the first thing I'll tell you is the useful thing is that if you multiply an odd function and an even function, you integrate over all space, you get 0. So that's really handy to know. Let's kind of sketch out these functions. So y equals x looks like this, and y equals e to the minus x squared. It doesn't really matter that there's an alpha there or not for our purposes right now. What this function looks like is this. It's a Gaussian curve, if you're familiar with that. So, it'll be 1 at 0, and then it'll decrease to infinity on either side, but it's symmetric. That's the important part here. So an odd function is one where if you swap from the positive side, right, so if we pick some value, say this is 5, and let's go to negative 5 on the x-axis. So at x equals 5, y will equal 5. At x equals negative 5, y equals negative 5, right? So if we swap, so if we take negative y, we get negative x. So an odd function, you'll switch the sign if you switch the sign of the x value. An even function is different. So if we go from, say, positive 5 over here and say y is equal to, I don't know, this is going to be some random value. This is not going to be correct. But say it's like 0.67 or whatever. If we go to negative 5, we get the exact same value. Right? Whatever the value was on the positive side is the same on the negative side. So if we take negative x, we still get the same value of y. So what's useful here is that if we integrate over all space over an odd function, so all the area on the positive side will be canceled out by all the area on the negative side, because this side will be positive area, this side will be negative area, and overall we get 0 if we integrate over all space. So I'll be more specific, from negative infinity to positive infinity. Whereas if we integrate over an even function, we get not 0. We don't know what it will be. We have to actually do the math. So if we multiply an odd function and even function together, too much zooming here, right? So if we multiply an odd function times an even function, what we'll get overall is an odd function. And so if we integrate over this odd function, we'll get 0 overall. And you can, if you can imagine multiplying these together, and if you want, I would recommend actually taking a graphing calculator or Google or Wolfram Alpha and plotting x times e to the minus alpha x squared, pick some value for alpha, it doesn't really matter, and show to yourself that this overall, if you multiply these together, you get an odd function and the integral will equal 0. So this ends up being a really useful technique that lets us solve some integrals really quickly by symmetry. We can't always do it that way, but that lets us figure things out. So just general properties for when we're talking about functions: an even function times an even function will give us an even function. An odd function times an odd function will give us an even function. And an even function times an odd function will give us an odd function overall. And so this is similar to if we took, say, positive and negative numbers, right? If we had a positive times a positive, we would also get a positive. Negative times a negative would also give a positive, and positive times negative would give negative, right? And so this is a really useful technique, that I just wanted to go over. And so especially when you're dealing with integrals over, like negative infinity to infinity, it helps if you can quickly say whether it's 0 or not, to know whether you have to do more work. If you know it's 0, then you're done.